We're going to be moving on to a new subject today, but there's a few little things I just wanted to clean up. We were talking Monday about rational functions. And I don't really need to say this, because this is just things that we've done before. But I think putting them together might be helpful. We saw on Monday that the function 1 over x kind of looks like this. X and the y-axis are asymptotes, and the book wants to make a point about a certain kind of function that might not be obvious what's going on. Look at f of x equals 2x plus 3 over x plus 1. Well, obviously a rational function, you can see it's going to have an asymptote, vertical asymptote at -1. You can figure out the end behavior. We're coming in so quick, I can't stay ahead of it. Let's see. So the idea here is we can rearrange this a little. We could do a long division. And that's 2, so 2x plus 2, 1. So this becomes what? It becomes 2 plus 1 over x plus 1. And I want to write the 2 on the other side. So why am I writing it this way? Well, remember when we were doing transformations, specifically shift transformations? Whatever 1 over x plus 1 is, this function is just that raised 2, right? All right, well, what about 1 over x plus 1? It looks a lot like 1 over x, except we've shifted this which direction? In which axis? In other words, the x? Yeah, the x-axis. And which way do we shift? When we see added 1 here, is that shifting the function over to the right or over to the left? Left. Okay. So really, what I have is this function, except we're going to shift it up 2, and we're going to shift it over 1. And since I'm a little lazy here, I'll just see if I can find this. Ah, there it is. So you can see, again, the dotted line is 1 over x, but the dark line is the same. It's just the same function shifted. So, you know, everything we learned about shifting functions applies to rational functions, too. You have a rational function that you know, and then you have a new function which is just that shifted. It should be fairly easy to figure out what it is. Okay. I guess we're just going to do one more example of a rational function. We'll try and use all the features we've learned. So the function we're going to just try and we're going to graph, and we're going to look at its features is f of x equals 2x squared plus 7x minus 4 over x squared plus x minus 2. And let's do this in an organized way. Let's first try and gather all the data we can about this function. Well, we probably should start by factoring the p of x and the q of x, right? So this is going to factor nicely using reverse FOIL. It's going to be plus 2 and minus 1. Is that right? Look right? P of x is going to factor nicely too, but not quite as nicely. So it's either 2 and 2 or 4 and 1. Well, 2 and 2 come out even, and this is an odd number. So now I have to figure out where does the 4 go. I think the 4 goes here and the 1 goes here. This is plus and this is minus. Okay, so what does this tell me about vertical asymptotes? Where do I have a vertical asymptote?
Is it 1 and -2?
Right. X equals 1 and x equals minus 2. Okay. That's a good start. How about zeros? What are the zeros of the function? Where does it cross the x-axis? Albert's not here. What about it? Where are the zeros of this function? Well, how do I find the zeros? Somebody's got to be scratching their head here, right? I have f of x equals p of x over q of x, and I want to know when it's equal to 0. What am I going to look at? I'm going to find out where p of x is equal to 0, don't I? This is my p of x here, right? Where is that 0? Yes?
1/2 that
She beats you by 1/4 of a second. I remember that. You know, when you're racing, right? Say again?
1/2 and -1.
1/2 and -1. Is that right?
-4.
I'm sorry. -4. Okay. What about the y? You get first dibs if you want. What's the y-intercept? The y-intercept is where f of x, I'm sorry, where f of 0 is. What's that?
2.
2. Okay. And what else do we want to know? We want to know what the end behavior is like, right? What do I want to look at? What do I want to look at to find the end behavior of this? Right, as x gets very large or very negatively large. Remember we were talking about end behavior? There are 3 possible kinds of end behavior on a rational function like this. So what do we have to look at? Look at the leading terms, right? Just 2x squared and x squared. What does that tell us? Yes?
A divided 2 divided by 1.
Well, yeah. I mean, as x gets very large, these become insignificant, so you end up with just 2 over 1, right? Okay. So what does that tell us about the end behavior? Does anyone remember if the end behavior is kind of a constant? What does that mean for the function? I mean, you might recall that if it's like something over x, well, we get an asymptote at 0, right? Because it's just getting smaller and smaller. And if it's something like, say, 2x or x cubed or whatever, that means it's acting like just a regular polynomial. You know, if it's odd, it kind of goes up and down, and if it's even, it goes up and up. Unless the coefficient is negative, it's upside down. What happens if this is going to a constant? What happens then? I'm sorry? Horizontal asymptote. So I'm having trouble spelling it just like this. There we go. Okay, so now we have all this information. We can start. I'm going to put a graph out here, put a scale on it, and draw in things that are relevant. So we know we have vertical asymptotes at 1 and -2. Figure out where the function is in a minute. We've got zeros at -4. Right, and a half. So the function is going to go through these points. We've got a y-intercept at 2. Okay. And we know there's a horizontal asymptote. One thing, I guess this goes along with there being a horizontal asymptote, is you know that the function is not defined at 1 or -2, right? So there'll be kind of, it'll be disconnected, right? It won't be continuous across there. Okay. All right, let's try and hone this down. So we know there's a horizontal asymptote at 2, but we don't really know, does it come from above or below? Right? So if we plug in a large number here, we could just pick, say, 10. So we get 200 plus 70 minus 4 over 100 plus 10 minus 2. So that's 264 over 108. So this is greater than 2, right? So we know as we're going out here, we're coming from above. Similarly, if we look over here, we plug in negative 100, negative 10, we get, again, 200, but now minus 70, minus 4, and 100, minus 10, minus 2, so what's that? 30, 124, 90. 89, 88, is that right?
126, 260. 126.
Oh, wait a minute. Wait.
266.
Yeah, I subtracted wrong. That's 130 minus 4, 126, and 90 minus 2 is 88, right? I'm scratching my head because I thought it was otherwise. But I might be wrong. It's gonna come from below. Okay. Well, we could do a little more work here. We could find out, well, it looks like this is going to go through here. We could see that this asymptote is going to go down, right? This one is going to go up. We have to plug in some values. And then we just need to know what does the function look like in here. Well, we know there's the 0 here, and there's the y-intercept here. And again, if you plug in values close to 1 on this side, you'll see that it's going to go negative. And similarly, as we get close to minus 2, it's going to go like this. No, that's not the most beautiful diagram. I guess that's why we have graphing calculators. Right. So here's Desmos's version. That's asymptote 1, vertical asymptote 1, vertical asymptote 2, and horizontal asymptote. Okay, so that's, yes? It came from a student. No, you find it by plugging in 0. So if you plug in 0 here, you get minus 4 over minus 2, so you get 2. I said that just in case it turns out wrong, and then it's not my fault. You see. No, that's a nice feature. You know, in this case, it kind of fills in, except my artistic, I guess, call this a spleen drawing. Okay. Any questions about rational? Yes.
How did you get that horizontal asymptote?
So I looked at the end behavior, and I looked at what happens when x gets very large or very negatively large. Okay, when x gets very, very large, the x squared dominates this, right? Same thing down here. X squared is going to dominate at x and minus 2. So what we're left with is just 2x squared over x squared, which is 2. right? That's how I know there's a horizontal asymptote. I don't know, we never reach the asymptote. I don't know where it's coming from. That's why I have to, find a value or, find something else about the graph that's going to tell me how that's working. You can always plot points, right? That's the, surefire, the tedious method. I mean, that's essentially what our graphics program is doing here. It's just plotting points. Okay. Any other questions about rational functions? We're going to move on. Yes?
What if it was what if it was x to the fifth over x to the third?
Okay, that's another case. It's x to the fifth over x to the third plus other stuff. Okay? Then in the extremes, this is going towards x squared. So in that case, what you'd expect that y equals x squared. Right? You'd expect, not necessarily in the center, but as the function gets far out, it's going to start looking more and more like this on the ends. That's kind of a good catch-all. If you have this situation, if the polynomial px has a greater degree, then there's some polynomial we look at, like x squared or x cubed, that as we get towards the edges, it's going to look like. Does that make sense? It's almost common sense, except it's math, so it's not common at all. All right. Now we move on. Let's see. Leave that for now. We're now moving into Chapter 4. Chapter 4 is about exponential functions and log functions. But before we get into the math, I guess you can look at it however you like. It's a puzzle, or it's a problem, or it's a challenge. Okay, so listen up. In the future, we're interviewing at a super corporation called Apple, Google, Facebook. They've all merged. It's the best place in the world to work. You get the best benefits, the highest salaries. You want to get hired. You need to show you're good at math by answering the following question with the smartest answer. Otherwise, they're going to find somebody else. So now you have two choices. They're going to say, what do you want your salary to be? Here are the two choices. Choice number one, you start at a penny a day. The first day you get a penny. The next day you get 2 pennies. The next day you get 4 pennies. So every day your salary doubles. And it's going to do this for a month. And then from then on, that's, you get that amount you get. Choice number 2. Now this sounds really good. You get $1 million a day. You want door number 3 or door number 2? Okay. And you're guaranteed employment for 1 month. And you have to choose right now. Okay. So who wants the penny a day? Okay, Paul. Okay, Aaron. Okay, all right. Who wants the $1 million a day?
It's 2 years 30.
I guess the rest, right? It sounds good, doesn't it? $1 million a day. That's in 30 days. That's going to be $30 million, right? Fantastic. Okay. Only half of you get to work for Apple and Facebook. Let's take a look. Right. So for choice number 1, well, the first day you get 1 cent, right? The next day you get 2 cents, 4 cents. So what you'll get on that day will be 2 to the n, where n is how many days, right? You get all the other stuff too. We'll look at that. So let's ask, how much are we going to get? Call this f of n. Let's call it s of n, since it's salary, right? Salary of n equals 2 to the n. And so we want to know, what's your salary on your 30th day? All right. But before we calculate that, let's do the other calculation. We already did it. Right? The other calculation is 30 days, $1 million, that's $30 million. Boy, does that sound good. I said this was the future, right? You know, a cup of Starbucks coffee is going to cost you like, $1 million, so it's not really that much. But it's inflation, and people taking economics here can explain that. Okay, so how much are we going to make here? All right, 2 to the 30th. No. Anybody have a calculator? With an exponential function? Good. Yes. Have you figured it out already? How many pennies do you get on the last day?
Well, I can write the number
2 to
down.
the 30th.
Write the number down.
Yeah.
1 0 7 3 7 4 1 8 2 4.
That's a lot of numbers. Okay, so the decimal point goes here, and then comma goes here, and comma goes here. But the day before you're going to make like 5 million, right? The day before that you're going to make 2 million, 1 million. Oh my. Are you sure?
2 to the 30th?
2 to the 30th. I mean, the reason I'm suspicious is I know that 2 to the 10th is 1024. It's about 1 million. So it should come out about 1 million, about 1,000. Oh, you're right. I guess I was wrong. I guess you should have taken the $1 million a day. Yeah. But it's surprising anyway, isn't it? Right? How did we get up that high with pennies? Yeah, I did this wrong. I forgot about the decimal point. Okay. Why is this surprising? Because what we've got here is an exponential function. I think I'm going to update this. It's an exponential function. We're going to talk about exponential functions today and for a day. Okay, so what's the definition of an exponential function? It's a function f of x equals a to the x, where a is greater than 0, and a is not equal to 1. If a is 1, it's kind of a boring function, right? It's just 1 all the time. 1 to anything is 1. If a is greater than 1, then f is increasing. F is an increasing function. It increases everywhere. What does that mean? What is an increasing function? Anyone remember a definition? Okay. This actually, right now we may have a feeling for it, that's probably good enough. But a good definition is if A is greater than B, that implies f of A is greater than f of B. That's an increasing function. A decreasing function would be just the opposite. If f is greater than B, then f of A is less than f of B. If A is less than 1, that is between 0 and 1, then 1 over A is greater than 1. What am I trying to say here? I guess what I'm trying to say is A is less than 1, then 1 over A is greater than 1. And I'm just going to call B 1 over A. So my function becomes what? Becomes f of x becomes 1 over B to the x. I'm not where I want to be. That's okay. If A is between 1 and 0, then f is a decreasing function. So, for example, f of x equals 1/2 to the x, right? If I plug in a large x, my function gets very, very small. Another thing you should be aware of is exponential functions are 1-to-1. Let's take a look at a picture of an exponential function. Just the function, our penny function, 2 to the x. What is a 1-to-1 function? Someone tell me what a 1-to-1 function is? Or something about a 1-to-1 function? Yes, Ingrid?
For every x, there's only one y.
For every x, there's only one y, right? Does anyone remember the name of the test you can do? See that? Hey, 3 voices intersecting. One at a time. Somebody, raise their hand. Whatever. What test do we do? Yes?
Vertical line test.
Well, it's the other one. Vertical line test tells you it's a function, right? This is the horizontal line test, right? You put a horizontal line here, it just goes through one point, we're 1-to-1. Something else about 1-to-1 functions that's going to come in really important on Friday. If you have a 1-to-1 function, you have a blank function. You know what blank is?
Exponential?
No. A 1-to-1 function doesn't have to be exponential. Exponential functions are 1-to-1. But if you have a 1-to-1 function, have an inverse. Remember? You can have an inverse. And these will have an inverse when we get to on Friday. Okay. One other thing to notice, this has a y-intercept, right? 2 to the 0 is 1. That's pretty common with an exponential function. Another thing to note about exponential functions, if you compare, say, increasing exponential functions, they're all kind of the same shape. They just, okay, so this is comparing two functions, 2 to the x and 4 to the x. The only difference is how quickly one of them rises. There's something else you should notice comparing these functions. If I look at f of x equals 4 to the x, what is that? That's 2 squared to the x, which is just 2 to the 2x. That is, it's just a transformation between them, a stretch transformation. All I have to do to get 4x is to stretch 2x. Times 2. Since we're looking at transformations, here's a question. What would multiplying an exponential function times a value? So 8 times 2x we'll look at. On one hand, we know that's going to stretch the function in the y-axis. But take a look. This is just 2 cubed times 2 to the x, which is 2 to the x plus 3. Well, what kind of transformation is that when I just add a value to the x component? We saw that just a few minutes ago. What happens to the function? Shifts. It's just a shift to the left. So that tells you something interesting about an exponential function, which is if you multiply it by a value, on one hand you're stretching it upwards, but you can also look at it as just moving it. Right? In this case, because we multiply by a number greater than 1, we're moving it to the left. If we multiply it by a number less than 1, we move it to the right, because it would be minus. Okay. Okay, so the graphs I've shown you have been increasing exponential functions. What about a decreasing function? Well, what's that going to look like? It's going to look just like an increasing function, except flipped around the y-axis. Now, that makes a lot of sense if you realize 1/2 to the x is just 2 to the minus x, which itself is just a transformation, it's a reflection, right? So if you take a look at this function, it's just a reflection around the y-axis. F of x equals 2 to the x. And then, you know, just for completeness, what happens if you multiply the whole thing by minus? Well, if I was to take this function and multiply it by -1, right, I get -2 to minus x. Well, that's just a reflection over the x-axis. Okay, so that's kind of the rough outline of what exponential functions are. I want to do a problem with exponential functions, and as it turns out, I actually had to use this knowledge about 6 months ago. How many people here have cats? You have a cat? Anybody have a- Oh, good, okay. So, does anyone have an old cat? That's good, because if they're young, they're around for a long time. So I have lots of cats, and one of my cats got a condition called hyperthyroid. This is a condition that people get too. They get a tumor. It's not a cancerous tumor, but it's a benign tumor on their thyroid. And their thyroid grows, and you start producing too much thyroid hormone, whatever that is. And that kind of regulates things like how hungry you are. So the cat doesn't get hungry, and it stops eating. And it's not good. But there's a really unusual treatment. You inject the cat with something called iodine iodine 131. That's an isotope of iodine. I don't know if you know, everybody needs iodine. And does anyone know where you get it? Usually? Yeah, look, next time you're at home, look in the pantry at the salt container. Say iodized salt. Right? They just put iodine in your salt so you get enough. Otherwise, you know, your neck gets really big and you get a goiter, and it doesn't happen anymore. Okay, so I have this hyperthyroid cat. They're going to inject him with iodine 131, and the thyroid collects your iodine. And now your hyperthyroid. I know this isn't a biology class, but just go with me for just one more minute. So your thyroid gland collects the iodine. It's radioactive. And it starts killing off the tumor because radiation tends to kill things that grow fast, you know, quicker than things that don't. And they put it in a very exact amount. They know just the right amount. And it kills off most of the tumor, and the cat is cured. But there's a problem. See, your cat still has radioactive iodine in it. So the litter is radioactive. It's not really that dangerous, but you can't throw it out. You throw it out, the garbage, they actually have radioactive detectors. And they'll, you know, so you can't do that. So you have to store it for a while until it's not radioactive. And that's the question. That's the question we want to look at. So radioactivity has a nice real-world problem to deal with exponential functions. And so I looked up on the web, and I found out that the half-life of iodine 131 is 8.02 days. Does anyone know what a half-life is? Do you have a question? No. Half-life. Anyone know what the half-life of a radioactive material is? Yes.
It's like half of a life.
Well, yes. Well,
Like half of it's gone.
No, it's not the 1%.
they're laughing, but they didn't have anything to say, right?
Isn't it like when half of it's gone?
Exactly, right? So, like if I have a pound, you know, I have a pound of radioactive iodine 131. 8 days later, I have half a pound. And then 8 days later, I have a quarter of a pound. It's really weird. How does the radioactivity know, you know, to decay just that right rate? I don't know, but it does. Okay, so how does that work? Well, we need an equation, right? So the iodine left after so many days is going to be the initial amount times 1/2 raised to the number of half-lives. Well, I want days, so that's going to be V over 8.02. In other words, every 8.02 days, I've got half as much left. That's my equation. I actually had to figure this out because I'm storing this stuff, you know, kitty litter in my backyard in a barrel. And what I decided was, when I have 1/1,000,000th the original amount of radioactivity, then I can probably get away with throwing it in the garbage. Okay, so how would we figure that out? Well, I of D over I want to be about 1/1,000,000th. All right? Which is to say, I want 1/2 to the D over 8.02 to be about 1/1,000,000th. Now, on Friday, we're going to find out how we can calculate that real easily. But we don't know yet. So we're going to use trial and error. And for that, I created a table. Right. So here's number of days, and here's I of D over I naught. See, I don't really know how much they put in the cat, how many grams or micrograms. I just know that I want 1/1,000,000th the radioactivity left. So if I plug in 10, I get about 0.42. That makes sense. A little more than a half-life. You're a little more than half gone. So that's not enough, right? Let's go a little further. Plug in 100, and that comes out to 0.00018. So that's about 18 thousandths. Still not good enough. But I know that exponential functions grow really rapidly. If I put 200, I'm way beyond that point. So I'm just going to try 150. And that turned out to be 0.0000023. Okay, so now I'm down to 2/1,000,000ths. So I'll just go a little further, maybe another 2 half-lives. And that turns out to be 0.0000001. Okay. So after 160 days, I know the radioactivity has fallen. I really had to do this. I had a cat, bring him to the doctor, They leave him there for a few days. He comes home and had a big barrel of kitty litter in my backyard. Okay, so 160 days, that's what? Over 30, that's 5 months, 6 months, yeah. Okay, so that's an exponentially decreasing function here, right? Okay, there's some more interesting stuff about exponential functions. Remember the average rate of change of a function? Someone tell me, I have some function f of x, and I want to know the average rate of change on an interval a, b. Does anyone remember what that is? Yes, Carlos?
F of b minus f of a over b minus a.
Okay. Keep that in mind for a second. So, if I have an exponential function, and I pick some points close together on the function. This is really weird and neat. If I find out the average rate of change between those groups of 2 points, and if I plot them, plot these points, and then I draw a line through it, I get an exponential function. Ooh, that's kind of eerie. I can keep doing it too, right? This is an exponential function. I can find, like around those points, a little interval, and I find the average rate of change, and I still have an exponential function. So that's an interesting feature that you will run into, especially if you go on to calculus. It's very important. Now, it's not the same exponential function. Well, it's not necessarily the same exponential function. It will be stretched or, if you like, translated. Okay. I'm getting a lot of facts about exponential functions here. The next one is, this is a little, it may seem unnecessary, but it is necessary. Let's say, let me look again at my, f of x equals 2 to the x, right? And I want to think about evaluating that at various x's. So, if x is a number, an integer, that's easy, right? We know how to calculate that, right? If x is 2, it's just 2 squared. If it's 3, it's 2 cubed, that's 8. What if x is a fraction? All right, let's say x was 123 over 454. And I want to know what f of x is. I want to know what f of 123 over 454 is. That's 2 to the 123 over 454. Well, fortunately, we know what that is, right? It's the 454th root of 2 raised to the 123rd power. I mean, we know what that is, right? I could raise 2 to this, that's a big number. And then I could just kind of use my calculator, or I could trial and error. I could try and find out the 454th root. That would be kind of difficult. But I know what it is. But that's not the only thing I can plug in here, right? I could plug in something like square root of 3. So that would be 2 to the square root of 3. I ask myself, well, what is that? What is that? I mean, this is not a fraction, right? It's a decimal, it goes on and on and on. So I have no way of really finding some root, right? Well, here's what we do. I'm going to use a table to describe this. I'm going to take square root of 3, but I'm going to truncate it. I'm going to start as 1.7, and then it's 1.73, and it's 1.732, and so forth. And then I want to look at a number which is a little less than 2 to the x, that is 2 to the 1.7. And I want to look at something that's a little greater than 2 to the x, so 2 to 1.8. Okay, the numbers here are 3.2490 and 3.4822. All right, now I want to increase my accuracy a little. So now it's going to be 2 to the 1.73 and 2 to the 1.74. So these numbers are 3.3173, 3.3403. And I'm going to keep going, all right? I'm going to get 3.3219, 3.3241, and down here at the end of my list I have 3.3219, 3.3221. Oh, people aren't going to be able to see over this, are they? And then finally, down to 4 decimal places, 3.3220, 3.3220. These still aren't the same number. But what you see is, between these numbers, I'm squeezing down the value of this, right? The way we say that is, if you just keep increasing the accuracy here, this number gets squeezed between them to a limit. There's some value. Again, it's an irrational number, so we can't write the whole thing down. But that's how we find, logically, how we find 2 to some. You know, it could be pi, right? Let's 2 to the pi. You would need the same kind of process. Now, fortunately for you, you have a calculator. It doesn't tell you the exact number, but if we need an approximation, you don't really have to worry how it's calculated. I think we're almost done for today. Yeah. Okay, thank you. I'll see you all on Friday.
Nothing today. Huh? I learned nothing. I learned nothing today.